I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the quantum mechanics. After means at the end of this lecture, student will able to understand the de Broglie hypothesis, and also you can understand the construction working of Davison-Germer experiment. So coming to the de Broglie hypothesis. Actually, the de Broglie hypothesis explains about the dual nature of matter. So coming to the statement, matter exhibits dual nature. The material particles like electrons, protons, neutrons also exhibit wave nature. Actually, the wavelength associated with the material particles are called matter waves or de Broglie waves. So these are called matter waves or de Broglie waves. Now the wavelength of de Broglie waves, it is given by lambda is equal to h by mv. In this one, h is the Planck's constant, m is the mass of the particle, maybe electron, proton, neutron, whatever it may be, and v is the velocity of the particle. Say h Planck's constant, its value 6.625 into 10 power of minus 34 joule second. Coming to the de Broglie hypothesis statement once again, matter exhibits dual nature, means the material particles like electrons, protons, neutrons, they can also exhibit the wave nature. Here, suppose if it is a charged particle, it is accelerating with voltage V, capital V voltage. Then what is its energy? The energy is given by E, capital E is equal to small e into capital V. Small e, charge of the particle, and capital V, it is the voltage or the potential difference. Anyhow, if the charged particle or the particle is moving with velocity small v, v is the velocity of the particle. Suppose if it is moving, it contains the kinetic energy. The kinetic energy E or Ke is equal to half mv square. So equating these two, what we get? Half mv square is equal to E into V. From this one, we can write what is this mv. So that mv, it is equal to we get 2ev and small m, 2mev we get under root of. So lambda, actually the de Broglie wavelength is given by lambda is equal to h by mv. Therefore we get lambda is equal to h by root over 2mev. Yes, actually if the particle is accelerating with voltage capital V, we have to use the formula lambda is equal to h by root over 2mev, where capital V is the potential difference or the voltage. If the charged particle is moving with velocity V, then we have to use the formula lambda is equal to h by mv, v small v, velocity of the particle. Actually this lambda is equal to h by root over 2mev, it is only suitable for a charged particle. That charged particle may be electron or a proton or any alpha particle, whatever it may be, we can use it. And especially if it is an electron, you can use the formula lambda is equal to 12.27 by root over v. Directly we get this one in angstroms. 12.27 by root over v. V is the voltage that is accelerated, that electron is accelerated with voltage v. Of course, m is the mass of the electron. We can take 9.1 10 power of minus 31 kilograms. H Planck's constant 6.65 10 power of minus 34 joule second. Substituting all these values, you will get this one 12.27 by root over v. Directly you will get this in angstroms. Generally 1 angstrom is equal to 10 power minus 10 meter. So in the former formula lambda is h by root over 2 mev, the wavelength units you will get in meter. Here we are getting directly in angstroms. So anyhow, you can use different formulae of the de Broglie wavelength. If it is moving with velocity small v, you can use lambda is equal to h by mv small v. If it is accelerating with any voltage capital V, you can use the formula lambda is equal to h by root over 2mev. It is suitable for any charged particle. Especially it is an electron, then you can use the formula lambda is equal to 12.27 by root over v. So you can use this formula only for electrons, not for any other kind of charged particles. Anyhow, this is the de Broglie hypothesis. Actually, as per the de Broglie hypothesis, if an electron is moving with velocity v, it is describing the waves, the de Broglie waves. Generally, how do we prove this one? This existence of matter waves has been proved by one experiment or several experiments. Out of them, there is one experimental proof given by Davison and Germer. It is called Davison-Germer experiment. By using this experiment, we can prove the existence of matter waves or the electron waves, whatever it may be. For this experiment, the schematic representation is shown here. This is the experimental arrangement for this or diagram for this one. And say this is the electron gun. In this experiment, there is an electron gun. It produces high energetic sharp beam of electrons. Generally for this one, high means some voltage is given, and that electron gun functioning, it produces high energetic beam of electrons. Finally, these electrons will strike a target. This is a target, that is actually a single nickel crystal. The target is the single nickel crystal. So after striking this single nickel crystal, electrons actually will be scattered in different directions. Of course, to collect these electrons, to receive the electrons, there must be a collector. Here one collector, here this is the collector. Collector is mounted on a circular graduated scale. That collector is actually a coaxial cylinder. This kind of coaxial cylinder is there. Inner cylinder and outer cylinder, these two are insulated from each other. They are held at some negative retarding potential. So that if the electron beam is entering, what happens? It will oppose the incoming electrons actually. It will oppose. But one thing, we keep some negative retarding potential so that what happens? Only the high energetic electrons or the primary electrons, they are produced from the electron gun and scattered by the nickel crystal. They will be scattered and they will enter the chamber. Otherwise, because of the collisions of the electrons with the nickel crystal, secondary electrons may be generated. They may enter the chamber, means collector. They may produce some unwanted results. That's why to stop this one, we are keeping this one at some negative retarding potential. Anyhow, these electrons will enter the chamber. Means that collector or Faraday cylinder, we call that as Faraday cylinder. This can be kept at different places by means of a circular graduated scale, so that at any place electron beam enters the chamber and that electron beam will produce the current. Actually, this Faraday cylinder is grounded through a galvanometer. It is grounded through a galvanometer so that these entered electrons will produce some current there. Why? Because current is nothing but flow of electrons, flow of charges, flow of electrons. That's why they will produce some current here. You can keep the Faraday cylinder or collector at different positions, at different angles, and different electron beams will enter into the chamber and they will produce different currents here. So after that one, if we plot a graph, observe the voltage is taken. Okay, the galvanometer currents are taken on the y-axis. Current is a measure of intensity of the electron beam. Actually, more electrons enter, say, more current they will produce. The current in the galvanometer is a direct measure of electron beam intensity. Here, the electron beam intensity is taken on the y-axis and the glancing angle or the angle is taken along x-axis, say. You observe at a particular voltage 54 volts, a 54 volts, you observe there is a considerable bump in the graph. At other cases, the bump is not that much observable. That's why this kind of one data we got. Means the accelerating voltage V is equal to 54 volts at the angle 50 degrees. There is a considerable bump in the graph. From this data, what can we say? From this data, how can we prove the existence of matter waves, or how can we prove the de Broglie hypothesis? For this one, you observe First of all, if the electron is accelerating with voltage capital V, how much voltage? It is 54 volts. If it is accelerating with 54 volts, what is the de Broglie wavelength? Lambda is equal to 12.27 by root over V. Directly we get in angstroms. Therefore, what is lambda we are getting? 0.167 angstroms. This is the de Broglie wavelength or wavelength of electron waves. Okay, we got, say this is equation number 1. Some equation we got. Second way, observe, this is actually the crystal. So that nickel crystal, actually the nickel crystal, these are the crystal planes. They are acting like the rulings of a grating. Electron beam is incident and it is scattered. What is the scattering angle? We observed the scattering angle is given by 50 degrees, and just to take the normal, this will be 25, this will be 25. Then what is the glancing angle? It is making the crystal plane. That glancing angle will be 65. Why? Because total 90 minus, so 25, that will be, say, 65 degrees. That is the glancing angle. Now you take the Bragg's equation, Bragg's law of X-ray diffraction. What is that one? N lambda is equal to 2d sin theta. That is the Bragg's law. N lambda is equal to 2d sin theta. Now the first order bump we have observed. That's why you take n is equal to 1. You take n is equal to 1, lambda is equal to, you will get 2d sin theta. 2 into what is d? D is actually the interplanar distance. In case of nickel crystal, the interplanar distance is given by 0.91 angstroms. And what is the glancing angle theta? Already we have just seen it is 65 degrees. Therefore, lambda is equal to 2 into 0.91 sin 65. So, simplifying this one, we get this as 1.65 angstroms. So, for the first order Bragg reflection, lambda is equal to 1.65 angstroms we are getting. You observe, say this is equation number 2. From these two equations, we are getting the same kind of, here actually this is not 0, this is 0.19, okay, 1.61, this is 0.61, 0.165 angstroms. In both the cases, we get almost same kind of wavelength. So, two different concepts we have taken. That is, one is using the Bragg's law, n lambda is equal to 2d sin theta, we got lambda value, and using this equation lambda, that means de Broglie hypothesis, we got the same kind of value. Actually, that Bragg's law of X-ray diffraction is only applicable for the X-rays. X-rays are nothing but waves only, just like light rays. So, X-rays are waves. In the same way, electrons are also exhibiting the wave nature, we can say. Like that, wave nature of electrons has been justified, or de Broglie hypothesis is proved. So, in this way, we can give the experimental evidence of the de Broglie hypothesis by Davison-Germer experiment. Once again, just brief, I will brief this one. This is the experimental arrangement for the Davison-Germer experiment. In this one, there is an electron gun which produces high energetic beam of electrons. This high energetic beam of electrons will strike a single crystal, that is actually nickel crystal. After striking the nickel crystal, the electrons will be scattered at different directions. To collect the electrons, one collector is kept on the circular scale, and it can be movable from 20 to 90 degrees. So anyhow, you can keep this collector called Faraday cylinder at different positions. How much angle is there on the circular scale, you can just get it, and this is connected to a galvanometer and grounded. So the electron beam enters, this electron beam will produce the current in the galvanometer. It is a measure of electron beam intensity. Now, if the electron beam intensity or that galvanometer currents are taken on the y-axis, and say on the x-axis the glancing angles are taken on the x-axis, automatically you will get this kind of peaks. At a considerable first order bump is observed at the angle theta is equal to 50 degrees, at the accelerating voltage V is equal to 54 volts. and taking this data using the Bragg's equation, lambda is equal to 12.27 by root over v, we get some wavelength lambda. Taking the Bragg's equation and using that n lambda is equal to 2d sin theta, again determining the wavelength lambda, there will be a good agreement between these two values. Automatically we can say that just like the X-rays, electrons are also exhibiting the wave nature. So actually coming to the summary of this one, here in this article we have observed what is the de Broglie hypothesis, what is the statement, and what is the de Broglie hypothesis. Next one, so to prove or to verify the de Broglie hypothesis, we have taken one experimental evidence, that is Davison-Germer experiment, construction and working of the Davison-Germer experiment to prove the de Broglie hypothesis. Okay, thank you.